So we've seen how this first system is solved with a substitution method. And when we did, I made the point that it's not the most substitution-friendly system, because it would require us, as we saw in the last example, to first solve one of the equations explicitly for one of the variables. So get y by itself in one of the equations, or get x by itself in one of the equations, and then you can substitute. If we chose a different path, then we might not have to do that step. And the different path is called the elimination method. So let me hear from someone who did this problem with elimination. How did you start that process? What would it look like to solve this system as an elimination problem instead of a substitution problem? What's elimination look like?
I multiplied the top equation by -3.
Okay, so that's an interesting choice. Let's talk about it. So the first thing you did to get the process of elimination started is you multiplied the first equation, presumably on both sides, right, by -3. Let's write that down and kind of see what it looks like. So -3 multiplied by x, -3 multiplied by 2y, and -3 multiplied by 5, -15. So my question to you is, why in the world did you do that? How would you know to do that to get this process started? What's your priority? What told you in this problem that -3 was the right thing to do to multiply this first equation?
I wanted to get rid of the x's.
Ah, yes, right. So here is this is the price that you pay to use the elimination method. The price you pay is that it requires you to look at both equations at the same time and ask yourself, looking ahead, what we'd like is we'd like to be able to either add these two equations to one another or subtract one of these equations from the other. You can look at it either way. But we would like that when we do so, again, one of our variables needs to disappear. Our ultimate goal in any system of equations method that we use is we need to make a two-variable problem into a one-variable problem. If we can do that, then we know how to solve one-variable equations, and we can get the whole process. The snowball starts rolling down the hill, right? But until we eliminate one variable through our work, we can't get anywhere. So in the elimination method, what we do is we look ahead and say, if I'm going to add these two equations together, let's say, then I need the equations to be set up in a way that that kills one of my variables. And so Mike is saying, let's say I want to get rid of the x's to leave me only an equation with y in it to solve. Then what I need is I need my x's in these two equations to have equal and opposite coefficients from one another. In this example, +3 and -3. Because if that's true, then when I add those two equations together, how many x's do I get? -3 and +3 combine to give me 0. And so my x's don't survive that process of adding these two equations together because the coefficients were equal and opposite. But when I do that, I still end up with some y's. -6y plus y gives me how many y's? Yeah, -5. So -5y. And then -15 plus -5 gives me -20. But most importantly, my x's are all gone. My single variable that remains is just y. -5y is equal to -20, and so we have a single variable equation. We can solve for y by dividing by -5 on both sides and getting y equals 4. Well, that sounds familiar. That was the same y that we got using the substitution method. And then once we know that this is the value for y, we can again plug that value back into either of our original equations. Let's say I plug it into the first one this time, so that my new equation will become x plus 2y, and now that y is 4, we can plug in a 4 in there for y, is equal to 5. And then simplifying the left-hand side and subtracting 8 from both sides gives me my value for x. X equals -3, again, just like we found when we solved the system using substitution. So, much like with substitution, the trickiest step in elimination is the first one. The trickiest step is in figuring out what we can do to the system by either modifying one of the equations or perhaps even modifying both equations. We need to make it so that the coefficients of one of the variables that we single out, here we singled out x for elimination, that the coefficients become equal and opposite, so that when I add them together, that variable is gone. So maybe before we talk about the other problem, let's look at one more elimination example where we might have to do a little bit more work. So we'll come back to our other problem in just a minute here. But let's talk through this one. Let's say I have 2x minus 5y equals negative 9, and negative 3x plus 4y is equal to 5. So here's the system. And let's say I want to solve this system using elimination. Now what would we want to do? What does my process look like? Ultimately, where I'm going with this is I want to be able to add these two equations together. This is what makes it the elimination method. Add the two equations together to cancel one variable. But if I try to do that step first, and this is the most common error that I see students make when they try the elimination method, is they try and get ahead of themselves and they start by adding. Well, what's going to happen in this problem if I just start by trying to add? How many x's do I end up with? Negative 1. How many y's do I end up with? Also negative 1. I'll add negative 9 and 5. I'll get negative 4. And so when I add these two equations together, I don't cancel a variable. I still have an x and I still have a y. Which means that this new equation isn't wrong. It still describes the same relationship between x and y that the original two equations do. It just hasn't helped us get any closer to find the value of any one of our variables individually. So before we do that adding step, we need to do the modification step to make it so that when we add our two equations together, one of the variables goes away. So how can we do that, do you think, in this example? First of all, let's target one of our variables for elimination. Should we target x or should we target y? Which one do we want to get rid of here? There's no wrong answer to that question, by the way. Why? Sure. Why not? Why are we targeting y? Why not? So we're going to target the y's for elimination, which means that we want to do whatever's necessary to make it so that the coefficients of y become equal and opposite. So the opposite sign part we've already got taken care of, right? The y's have a negative 5 and a positive 4 as coefficients. So the sign part is working for us. What's not working for us is that the values of those coefficients are not the same, right? One of them is a 4, the other is a 5. So we need to fix that. This, by the way, is completely analogous to the question of how to add, let's say, the two fractions 1/4 plus 3/5 or something like that. What would be the first thing that, this is a digression, what would be the first thing that I would have to do to try to add these two fractions? We need a common denominator, which we can find using the least common multiple of 4 and 5. Yeah, exactly. So we would need to rewrite these as fractions with a denominator, a common denominator of 20. 20 is the least common multiple of the numbers 4 and 5. And so that least common multiple is the same thing that we're going to shoot for in these two equations to be our coefficients, our equal and opposite coefficients for y. Because we can multiply either of these equations by whatever we want to and still have an equivalent equation. Let's use that flexibility, let's use that freedom to multiply the first equation by something that's going to make the coefficient of y 20, and also the second equation multiplied by something to make the coefficient of y 20. So beginning with the end in mind, Franklin Covey calls that his first secret of highly successful people in the classic seven secrets of highly effective people. Begin with the end in mind. And here, our end is that we want our y to have a coefficient of 20, negative in the first equation, positive in the second equation, so that when we add those two things together, the y's are going to go away. So then just as if we were to balance these two fractions with a common denominator of 20, we have to ask the question, what do I multiply 4 by in order to get 20? 5. So that should be what I end up multiplying the 1 by, right? Well, same story up here. That means that what I want to do is multiply this first equation by 5. Oh, sorry, not the first equation, second equation. Multiply the second equation by 5. Because if I do that, the coefficient of y is going to go from 4 to 20. But if I multiply that by 5, I have to multiply that whole second equation by 5. So the right-hand side of that second equation becomes 5 times 5. The left-hand side of 5 times negative 3. There we go. Then what about the first equation? The first equation, y starts with a coefficient of negative 5. We want the new coefficient to be negative 20. So what am I multiplying that first equation by? 4. So see how it's the same set of skills that you have to implement when you're finding a common denominator for two fractions? We just need to take each of the coefficients of the variable that we're trying to kill and scale them up to the least common multiple by multiplying by whichever is appropriate to multiply by. Multiplying that first equation by 4 is going to give me on the right-hand side negative 36. And on the left-hand side, 2 times 4 is going to bring me up to 8. And so that is the first step. And again, when students make errors in this process, it's because they forget this first step. Multiply. Here we had to multiply both equations to make this happen. In the first example that you worked with elimination, you got away with only multiplying one of the two equations. But in general, you might have to multiply both to scale up to the least common multiple of whatever variable it is that you're trying to eliminate. But then once that's done, and that really is the hard part, now we can carry out the rest of our plan. Because now if I add these two equations together, how many, first of all, how many x's do I end up with? 8x minus 15x. Negative 7. And for my, for my y's, negative 20 plus 20, 0. So my y's have gone away, and negative 36 plus 25, I think that's negative 11. I thought I chose friendly numbers for this problem. I guess I didn't succeed in that. So then dividing x by negative 7, dividing both sides by negative 7 will give me a solution for x. X equals 11/7. And then I won't do this part, but we would just plug that number back into one of our original equations and then solve that equation for y, etc. Solve for y. But my main purpose in choosing this new example was to talk about that first step. And if you're going to make an error in this